Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Let's get started. So, we were talking yesterday about the different project data sets, and I got a little bit of the way through talking about the second one, but realised I didn't have time to finish, so we'll go over that again and do it properly, and then we'll head into the last chapter. Okay, so just before we do talk about the insurance data, I just wanted to go back to the data on the otters for 1 second. Okay, just want to go back to the otters for 1 second. And just talk a little bit about these groups. So you actually have 5 different groups of otters. They're different sizes and different compositions, and generally pretty straightforward. Group A has 1 adult female and 3 adult males. Group B and Group C each have 1 adult male, 1 adult female. Group D has same structure, but the 2 otters are brother and sister. Okay, and then the last group has 4 in it again, and these are young or younger otters. So you've got subadults and young adults. So a question I always get asked is, who's younger, a subadult or a young adult? The answer is the subadult is not yet adult. The young adult is adult, but is young. So the subadult is younger than the young adult. Okay? Not that that necessarily matters, but people always ask me what the relative ages are, and the answer is subadult is younger than young adult. Okay? The reason you might think these things are in there, and again, you know, this is again the great mystery of data. I think, as I said yesterday, data doesn't come with instructions. Not only does it not come with instructions, it often comes with red herrings, things that don't matter, right? You just don't know they don't matter yet, okay? So it might or might not matter that those 2 otters in Group D are siblings. It just might not make any difference at all, right? But you just don't know that yet. That's part of why you explore the data, okay? And the age of the otters might not matter either. That may make no difference to the way they behave. So, you know, it's one of those things where the data is what the data is, and you just have to sort it out from the best perspective that you can. Okay. All right. Oh, the one other thing I wanted to mention about the otters is something that people always get confused about, even though it's written here clearly. In the otter data, there's a list element called time. That is the time they are watched, okay? It is not the time spent grooming, okay? So it's just the time they're watched, not the time they spend grooming, okay? So let's be very clear on that, okay? So they're watched, so when they groom multiple times. It's not kept track of how long those sessions are at all, of grooming. They're just watched over a fixed time period, okay? So that's what time means. Okay, let's talk about insurance. So we got a little bit of the way through this yesterday, and I was trying to explain what the different variables are. So here's the structure, very, very briefly. So a person presents at an insurance company and says, I'd like to insure my house, please. The insurance company will say to them either, okay, we'll insure you, or they'll decline to insure that person, okay? Now, they're legally allowed to decline insurance on the basis of certain risk factors. So, for example, if your house is in a neighbourhood with a massive theft rate, they might say, no, we don't insure houses in that district because the risk is too high for us because of the high theft rate. Similar high fire rate, okay? So there are underwriting variables or risk factors that insurance companies are allowed to use to determine whether or not they want to sell you insurance. Okay? Now, in the city of Chicago, the government got involved and said, look, we think that the decline rates on insurance are too high. So they created this category of insurance under what was called the FAIR Plan, and that was if someone was declined insurance, then they could go on to what's called a FAIR Plan policy. In other words, the insurance company could charge them a higher premium, but it could not decline them this other type of insurance. Okay? And that's why in this data set, there's two variables. One's called VOLAN and one's called INVOL. So VOLAN, voluntary, that represents insurance that was sold freely by the insurance company. Person rocked up to the insurer, I want insurance. Insurance company said, sure, we'll sell that to you. That's voluntary market activity. Okay? They're happy to sell you the insurance. Involuntary market activity represents declined insurance that was then picked up under the FAIR Plan. Okay? So these are policies that the insurance company sold because they had to. That's why it's called involuntary. They had to under the law. Okay? So you can think of voluntary as being essentially insurance that was accepted straight up, and you can think of involuntary as a measure of declined insurance. Okay? So together, you get all of the possible insurance that's in the market. All right? And then you've got all these other variables: income, age of housing, theft, which is an index of the theft rate in each neighbourhood, fire, which is the index of how much fire activity there is, and race, which represents the percentage minority in the neighbourhood. Okay? So the game is to try and work out to what extent the variables fire, theft, race, age, income affect capacity to be insured. Now you've got two variables that involve insurance, so it's no secret that you're going to have to do something to combine those two variables to get a sensible response variable for this problem. Okay? So that'll be one of the first steps you'll have to take. And so I'm not going to tell you what combination to use, but a little bit of thinking about it, you'll work it out pretty quickly, I think. Okay? So start thinking about that. And then basically it's sort of like a regression problem in the sense that you've got now a response variable and you're going to relate that to the other variables. But you have a question in mind, and the question is, does race matter in a way that would indicate illegal behaviour by the insurance company? Okay? Now, if you just plot this measure of insurability versus race, you'll see race matters. But that's not the question. Remember, these variables interact. They're allowed to say, we don't sell you insurance because the theft rate's high. And maybe the theft rate's high in neighbourhoods with a high racial minority. Maybe that's a possibility. So there's correlation. So the game is the typical game that you play in regression, where you're trying to tease apart these variables and work out whether certain variables are important, given that other variables are in the model or allowed or whatever. So that's kind of the game. Now there's one extra wrinkle to this, which is this column here, zip code. And this refers to another piece of information you have, which is this map. So the zip codes are on this map. Okay? Now, two things. One's obvious, but I have to say it because one year this did not work out for somebody very well. So zip code, these numbers, they don't mean anything. They're like Canberra zip codes, right? 2601, it doesn't mean anything. If you live in 2601 and someone lives in 2602, that does not mean they're one better than you, right? It just means they live in a different suburb. So zip codes don't have numerical meaning. So don't use these things in the model as numbers, okay? If you do, I will think bad things about you. Now one year, I have to tell you this, one year somebody used zip code as the response variable in a regression model. and produced perhaps the most meaningless 8 pages of drivel I have ever read. Okay? Now remember how I said to you that as long as you hand stuff in, you'll pass? Unless you do that. If you do that, you'll fail. And you'll go down in a screaming heap fail, right? You'll get as close to 0 as I can give. Okay? So, and okay, look, I get it, right? The person did the assignment on the last day, zip code's the first column, of course it's the response, fit a model, blah, 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 right? So obviously they didn't understand any of the course because you wouldn't do that if you knew anything about what was going on. But here's the postscript to the story, which is even funnier. After they failed, the next semester they came to see me and they argued with me about why they were right and I was wrong. And I could not find words to explain how stupid what they did was. Because, I mean, and everyone in the room knows, I mean, I'm not saying they're stupid, I'm saying what they did was stupid. Because it just makes no sense. These things they're not numbers. Well, they are numbers, but they don't mean what numbers mean. Okay, so anyway, so I'm going to put that out so that everybody knows, don't do that. Please don't do that. Please don't do that. Okay? All right. Last thing I'll say about this is how do I want you to use the map? Look, I want you to think about creative ways to use it. One thing you might want to do is print out the map. You might even be able to download a version of this somewhere. I have seen downloaded versions which don't look quite as bad as this one, because this is a scan. And get some colouring pencils, and colour in zip codes that have certain characteristics, like high race, low race, that kind of thing. Okay? Or high theft, low theft. Okay? Just see if you can think of ways in which you can understand the spatial aspect to this data. Okay? Now, I don't expect complex uses of the map. And if you don't use the map at all, you can still get an answer that's decent. Okay? But if you can think of a way to use the map, and you can do something a bit creative with it, then that could work out well, right? Okay? So I don't expect you to be using any kind of spatial Kriging model or anything like that. Again, if you want to, you can, but I don't expect it. And I just want you to have a think about how spatial dependence, might affect the way you think about the relationships involved. Yes, sir?
Is there any data representation of the locations in that? Or is that the only?
That's what you got. Yeah. I mean, you might be able to download something because there's plenty of GIS data out on the web. And as long as it's Chicago and it's the same zip code, you'll be cool. Probably won't need to, but yeah.
So, for example, with Urban Fire, you said it's like an index, right?
Yes.
So, how could we interpret that? Is it like if it's 1,000 events or 100 events?
I think it actually says here, let me have a look. So it says, where are we? There's a lot to read, isn't there? The Chicago Police provided theft data and the fire department provided fire data. These data are the number of incidents per 1,000 housing units. Yep. Yep. So, cool. Alrighty, so that's the insurance data. Okay, so you've got these two choices of data sets. Let me just talk very briefly about how you might choose. Look, I know that a lot of people end up in GDA through their actuarial degree. If you're an actuarial student and insurance is something you're interested in, the insurance data might be quite interesting to you. So that's thing one. Thing two, the insurance data lends itself to a regression style analysis. So if you kind of feel that regression is something that you've done regression's in most of our courses, isn't it? So if you feel like regression's something you're quite comfortable with, you might decide, okay, I think I can get my head around this one pretty easy. The data's just in a matrix, so there's no messing around like with the otters where there's a lot of equals and all this sort of nonsense. So those might be the kinds of considerations you have for the insurance data. The otters, doesn't really need modelling of any kind particularly. It doesn't, you can do a lot of stuff with simple tools that we talked about early in the course. And so it's sort of a bit more descriptive in the way you might tackle it. It's kind of fun, and my experience is that people tend to choose the otters because they're so damn cute, right? Because, and look, you go to me, well, really? And I go, look, I was using the wrong mouse. But I'll show you, right? Because river otter. Okay, we go river otter, and then we've got to go to Google Images, right? And who would not love this? See? Look at that. Look at that. He's saying, do the otter data. Please do the otter data. He looks pretty nicely groomed too, doesn't he? Actually, he looks a little scary, I've got to say. Anyway. So it's up to you. One last piece of advice. Don't do both. Right? Oh, one year someone did both and handed them both in and then complained when I gave them the lower of the 2 marks. Why did you do that, they said. I said, I don't know, I'm just being mean. So don't do both, waste of time, okay? You might start both and just see which one's going better for you, but definitely don't write both up and definitely don't hand both in. That'll just confuse me. And I'm very easily confused, as you by now know. Okay. Yeah.
For the reef, we have the list of which number means which.
Sorry, which?
I mean the reef proper. So do you have the explanation of which number refers to?
Oh, yeah. So if you on the website there with the project description, it talks you through what all the columns are. Yeah. No, that's cool. That's cool. Okay, well, we're going to head into the last chapter of the notes. One of the weird things about this course is that, the last assignment's all about this chapter, so we're about to start the stuff for the last assignment. You'll have about a week to do it, and that's about right in terms of how hard it is, so don't worry too much about that. Because of that, we'll actually finish the material for the course probably a week and a half before the end of the semester. And then I'm going to dedicate the rest of the semester to having fun. Yeah? I know. Well, I'll still have lectures, but they'll be fun. Anyway, I can see how much you're all looking forward to that. Outstanding. Okay, let's talk about time series. Now, let's be very clear here. You can do whole courses on time series, right? 13 weeks of nothing but time series. We are going to spend about 2 weeks on it. Week and a half to get most of it done. So you've got to believe we're skimming the surface of time series here, okay? We're just going to get the barest idea of how to analyse basic time series, okay? And time series is a funny old thing, and I'm going to show you a time series. This is alcohol sales in Australia, okay? I think it's in millions of units over several years. And I'm just going to show you what a time series looks like. There it is. So this is between 1974 and 1990, measured every quarter, right? So it's measured in spring, summer, autumn, winter, okay? Measured every quarter, alcohol sales. So in some sense it's like a regression, right? Because you've got an X variable and you've got a Y variable. And the Y variable is the thing that's changing through time, and the X variable is time itself. And this looks like a regression setting, except for 2 things. The first thing is that time behaves in a particular way, right? Tick, 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 and equispaced, okay? That's the first reason. So it's not random at all, it's fixed. And the second reason it's different to a regular regression setting is that time is pretty much never, ever causal, right? Changes in time don't cause changes in the other variable, unless there's some particularly simple relationship. If you plotted my age versus time, yes, that's causal, right? And you'd get a straight line. I hope, until I die, then it flat. Not good. Okay, and you'll notice, so I've got dots here on the page, and you'll notice I joined the dots, and the reason I joined the dots is we want to think about the flow of the data through time. Okay? So, this is alcohol sales in Australia measured every quarter between 1975 and 1990. I've joined the dots. The plot's pretty simple. It's just a plot of the time values versus the alcohol values. Type equals B says put both dots and lines between them. Okay? All right. Now, let's talk about this data. Let's look at it with eyes that don't know how to fit time series models yet and think about what it's doing. Okay, so what's this data doing? What's this data doing? What's happening to alcohol sales? Are they going up? They're going down? They're going up then down? What are they doing? So, let's get our fingers out. All right, excellent. Someone's doing this. That's right, it is doing that. Okay, it's wiggling. So the wiggles are what's called a seasonal effect. What do you reckon? In summer, do you think alcohol sales go up? Because it gets hot. Yeah, cool. And in winter, do you think alcohol sales go down? Yeah, because it gets cold, right? I mean, they don't go down to zero. I mean, it's Australia, for goodness sake, right? We're all still drinking most of the time, but they drop because it's not as hot. So, you know, you might not sit in the afternoon sun and have a beer. You might instead lie down at home and under a blanket, not drink so much. So those wiggles represent a particular thing that's very repetitive, right? Every summer it's up, every winter it's down, spring and autumn in between. So that's one feature of the time series that's really obvious, the wiggles. Okay? The other feature of the time series that the wiggles makes it hard to see is this thing's going somewhere, right? It sort of seems to start a bit low here, then it sort of rises, then it maybe drops a little bit before it seems to rise again at the end. Okay? So again, if you're using your fingers, oh, very good. So use two fingers, yeah? So it goes sort of up a bit, drops a bit, and then just at the end seems to be coming back up. Okay? And it's good that you're using your whole hand because that sort of captures all that wiggling, all the wiggling's going on in here, right? But you've got the general drift of the series. And that general drift of the series has a name too, it's called the trend, right? So the trend of the series is kind of up, down, up. The seasonal part of the series is that wiggly bit that happens every year. And then what's left is what we would normally, in regression context, call residuals or errors. But here's a big difference. In regression, we assume that errors are independent, right? And remember that independence means that every new data point brings brand new information, okay? In time series, the errors are not independent anymore. Data points from one to the next give you information because the past affects what happens right after it and on into the future. Okay? So there's dependence here. And we're going to have to model that dependence as well. Okay? Now, if the dependence was extreme, like really strong, then the errors would basically boil down to a series of numbers that you could actually predict very reliably from one to the next. So I think what we probably have here is weak dependence, but it's still dependent. And by dependent, I mean correlated, right? So in a normal regression problem where you assume independence, the errors are uncorrelated or independent, which means if I tell you that the first error is 0.2 and I ask you what's the next error, you don't know because I've given you no information that helps you tell me what it is. Okay? Whereas in time series, if I tell you the first error is 0.2, I've actually given you some information that might help you guess what the next one's going to be, if they're correlated. Okay, so that's the breakdown. We're going to go trend, we're going to go seasonal, and we're going to go irregular, we call it. Okay? All right. Now, in R, there is support for what's called a time series object. And that lives in the mass library, MASS. And there's a function in the mass library called TS, which stands pretty obviously for time series. Okay? So we're going to load the mass library, and then we're going to go Z is a time series taking the alcohol data. It starts in 1974 in the third period. So it starts in the third quarter of 1974. And the frequency is 4. This is the number of times the data is measured per year. Now, the reason that we turn this thing into a time series object is that once R knows that it's a time series object, look at how it displays it. If I just type alcohol, I just get the big vector of all the alcohol values, right? If I type Z, because Z's a time series, look how it sets it out. It sets it out by quarter and by year. So it's really obvious what's going on. 1974, third quarter, value's 1405. Then it goes up to 1606, 1518. And then it goes along each year, okay, until you run out of data. All right? So this time series object is a special kind of object. It carries temporal information, and then it carries scale information for the data itself. And the plot function in R is really smart. If you give it a time series object, it'll construct a beautiful plot that looks just like the one we did by hand a minute ago. So I just go plot of Z, type equals B. I've used plotting character equals a star here. I didn't have to use a star. I could have used, let's use PCH equals 1. That'll give me little circles. Okay, it looks exactly like what we had before. Now, what else do we normally worry about in regression? We worry about whether it's linear, and then we worry about heteroscedasticity, right? So when we looked at this particular data, what we did was we did this. We used our hand. This was to capture the wiggles, but the wiggles represent variation. And as you move from left to right across this data set, your fingers stay about the same distance apart. So this data set here looks pretty close to homoscedastic. Okay? Not all data sets have that character. One of the other data sets we're going to look at as we talk about time series is kiwi fruit sales in New Zealand. And let me just show you what the time series for kiwi fruit sales looks like. Looks like that. So they're going up, but the variance is growing over time. So again, if you did that thing with your hands or fingers, you'd have to be sort of really skinny down the left-hand side, and then it would explode, right? So it's sort of going boom, like that. By the way, you know, every data set tells a story, right? Every year, there's all these months where sales are 0. What happened? It's not the season of kiwi fruit. There's none growing, right? Life has changed, by the way. When I was your age, I know you love it when I tell stories like this. When I was your age, you go to the supermarket and you could get apples at a particular time of year, right? When apples were growing, and not at other times of year, right? Now you go to the supermarket, it's everything all the time, because they bring stuff in from all over the world, right? And you know it's happening, right? Because when I go to the supermarket, when I want to buy oranges, you know that it's orange season when they say product of Australia, and you know that it's not orange season when they say product of the United States, right? Because they're bringing them in until Trump puts a tariff on them, right? I'm sure he'll do that, although he is orange, so maybe he won't. Anyway, something will happen. So that's the non-growing season. So you'd probably expect these days that different things might happen to this data. Which brings me to another point, which is that for time series, one of the big goals is prediction. But again, you have to just control yourself and remind yourself that prediction too far outside where you have data exposes you to being more and more and more wrong, right? So most predictions aren't going to work too far outside where you have data. And, you know, even for this data, you know that's going to be true, right? Because this is kind of predicting that kiwi fruit sales are going to, you can see they're sort of going up, and they're right up at the end of the plot. Where are they going to go from there? Well, if you follow the pattern, straight up, but you know what? There's only so much kiwi fruit people want. That's not the way the market really works. There's a saturation point, and so that model's not going to work forever. Okay? Anyway, we'll talk about kiwi fruits later. But before we move off them, let me ask you a question. Who eats the skin? Who eats the skin on a kiwi fruit? It's a lot less messy if you do. It's a bit furry. Yeah, anyway. All right. Just curious. I actually eat the skin on kiwi fruits. Can you believe that? My son doesn't believe it. He thinks there's something seriously wrong with me. He might be right. I don't know. Okay. Mind you, his judgment that there's something seriously wrong with me is not only based on my kiwi fruit habits. It's pretty much based on everything I do. So that's life. Okay. What have I done now? I've added a low-S curve to this particular plot. Low-S is wonderful. Remember that low-S is a very robust method for fitting lines to data. And robust means ignores outliers. And those big high points look like outliers to low-S. And those low points look like outliers to low-S. And so it carves its path through the middle of this data and it kind of ignores the wiggles, which is really cool. And this low-S curve does what I hope your fingers were doing when I said, what shape does this thing carve out? Goes up, crests, falls, and then maybe at the end starts to flatten out or go back up. Okay? And the way you run low-S is pretty simple. You say low-S, you give it the x value. Well, the x value are the times, and the y value, or the vertical value, is the z. So low-S of times z and z, and that'll put the curve on the plot. Now, this is great, and we now have a picture of what goes on with this data set, but low-S, as we have discovered before, is not really very good for prediction because you don't get a formula, right? And so if someone says to you, cool, can you tell me what the alcohol sales are going to be 2 years on from now? And you go, oh, let me just plug that into my... Oh, I don't have a formula. Uh-oh. And you kind of got to guess what it does. So low-S curves are great for describing what's going on, but they're not really good for forecasting, and people want to forecast. So we're going to have to use models that are easier to forecast with. Okay? So what kind of models could we consider? All right, let's have a think about this. So, let's put the plot down on the page again. This mouse is driving me nuts. They're so terrified that someone's going to steal the mouse that they attach it to the desk so tight you can't move it. Ah, welcome to my life. Okay, here we go. There's the data again. All right. There's a really simple model for this data, okay? Straight line. So all I've done is I've said, here's my plot, and I've just added a line, which is a linear model relating z to time of z, okay? Now, RLM or LM, z tilde times z, okay? Linear model. Okay. Is this a good model? Is it a bad model? What do you reckon? It's okay. It's okay. Yeah. I mean, down here it's low, and up at the end it's high. It's kind of missing in the middle a bit, but it's going through it. Okay? It's not really going through the middle of the data, is it? It's kind of missing here, but everywhere else it's kind of okay. Remember, all models are wrong, some models are useful. This one's okay. It's not. I don't think it's particularly good, but it's not horrendous either. It's not a disaster. It's okay. All right. So we can probably do better than that. So what might we do next? Well, we could say, okay, maybe a quadratic will fit this okay, right? So let's go ahead and fit a quadratic. It's easy to do. We go RLM, z tilde, and we give it time of z and time of z squared. Okay? Simple thing to do. So let's do that. And let's put that, and let's whack the quadratic over the top of that. All right, what do you think? Better than before? Better than before? Who thinks it's better than before? Okay. Who thinks it's worse than before? Okay. So better wins, but there was a contest. People thought it was worse. Why is it worse? Why is it worse? Who wants to tell me why it's worse? I've got a couple of reasons why it's worse. Yeah. Yes. Absolutely. This thing goes up and then it comes down, and because it's a quadratic, is it coming back up? Never, ever, ever. Quadratics have one turning point, right? It went up, it comes down. Guess what it does next? Crashes into the ground, right? That didn't happen to alcohol sales. Okay? So it's not going to give you good predictions past where you've got data, even in the short term, because we don't think the thing's doing that. So it's worse in that sense. Excellent. It's better in the sense that it does seem to follow the data better than the other one, but it's got this structural problem, which is that it can't come back from where it's going. Okay? So we probably would not use the quadratic for that reason, because it really is a one-trick pony. All right, now, next thing I'm going to do is I'm going to fit a cubic model. And the reason I'm going to fit a cubic is because when we looked at the low S-curve, it went up, peaked, came down, troughed, started to come back up again. So a cubic function has two turning points, and so, yeah, maybe that'll work. Now, I'm going to have to be careful about the way I fit it, and I'll show you why. So you'll see here, the first thing I do is I go, where is it? It's up there. X is time of Z minus 1982. Why do I do that? Let me show you. Let me show you. I'm going to try and fit the model just using the cubic. So if I go RLM of Z tilde C bind time of Z squared and time of Z cubed, right? Have I got too many brackets? Yep, there we go. No? Oh, brackets. Yep, one more. Another one. You get this. It goes error in RLM, X is singular, right? Now, X is singular means that my design matrix, that is a matrix that's got a column of ones, a column of time, a column of squared time, and a column of cubed time, if that matrix has collinearities, then I get a singular fit. Okay? Now, we know this matrix does not have collinearities. It can't have. Z squared, a time of Z squared is not linearly related to Z. And time of Z cubed is not linearly related to either time of Z squared or time of Z, right? They're not linearly related to each other. One's a quadratic and one's a cubic. But R runs into this problem. It can't fit it because it thinks that they're linearly related. And I'll tell you why. If I draw a picture, I'll draw it over here. Have I got a pen? I do have a pen. Okay, so this is a picture of x squared, right? That's a picture of x squared. We can all agree with that? Okay, I've got values of x between here. They're between 1974 and 1990. So this is the part that I'm looking at. That looks like a straight line, right? It's not a straight line. There's curvature to it. We know there's curvature to it. It's the relationship between a square and its linear, and x and its square, okay? But for these really large values, because of the way R does arithmetic, it looks linear enough to it that it runs into problems. So there's a numerical trick that we can use that helps us with that. And the way we do it is we centre things so that we're closer to the middle of the curve than to the edge of the curve. Okay? So what we do is we centre time. In other words, we change Z into... So we change the time of Z into time of Z minus a year value that's sort of in the middle of the Zs. Okay? Now I chose 1982, so this data set went between 1974 and 1990, so 1982 sort of in the middle. I just chose my favourite year from the 80s. I know you weren't alive, but 1982 was a hell of a year. Okay, I think the Bee Gees were big. Actually, they were big for the whole 80s. Yeah. So, you're not working with me today. All my cultural references are so outdated, nobody gets them anymore. I feel old. Oh well. So we centre time so that instead of being out in the part of the place where it looks really linear, we're sort of down here where it looks more curved. Okay, and that allows R to fit the model. We don't actually change the model at all. Right? The model that's fit will be the same, but by centering time, the numerical fit is better. Okay? So now we fit Z to x squared and x cubed. All right? And the fit works. And now we can go ahead and we can do it. There's the plot. There's the cubic function added over the top. Awesome. Right. And just for fun, let's add the low S curve, lines, low S, times Z, Z, colour equals red. There's the low S curve. So, we look at that and we go, you know what, this looks good, right? It follows, they're pretty close to one another. Now there's some issues, right? Right at the edge there, the low S curve is kind of not going up and the cubic is, okay? They're a bit out down here, but you know, it's not too bad. It's a pretty good model, okay? And it's easy to write down, right? If I go fit dollars coef, right? I get these numbers here. And now I'm able to say, what's my model? My model is alcohol equals 1573.6 minus 1.7 times year minus 1982, right? Minus 1.22 times year minus 1982 squared, plus 0.177 times year minus 1982 cubed. So that's the model that I've ended up fitting. And the beauty of this model is, if you say to me, predict what alcohol sales are going to be in 1991 first quarter, so 1991.25, all I do is I put 1991.25 here, here, and here, hand calculator, right? Or I could do it in R and get a number. And that's it, right? Prediction's trivial for these kinds of models, whereas for low S it's unavailable, right? So that's really neat. That's really neat. Now, good model, bad model, better than before or not, okay? Again, there's better and there's worse. Right? It certainly fits the data quite faithfully, we think. So I think from the point of view of fit, it's probably a good model. From the point of view of prediction, well, be careful with polynomials, because in the same way that quadratic was crashing and not coming back up into the sky, this thing's going straight up into the sky eventually, and it ain't coming down ever. Right? And so there's that issue. It's not a big issue as long as you keep reminding yourself, if I predict too far into the future, I'll look an even bigger fool, right? So it's okay to predict what's going to happen tomorrow. It's crazy to predict what's going to happen in 2 years, because you'll just be more and more wrong, okay? And so these models can be used quite effectively for short-term predictions. And frankly, that's what most people want to do. Most people want short-term predictions, right? I mean, it probably has not escaped your notice that the government of Australia operates on the basis of predicting that there'll be a budget surplus 20 years from now, right? They know 100% that they are wrong, but people vote for them if they say that, right? So they're using the fact that predictions are wrong to make hay. It's crazy, right? Anyone who's done any statistics should be able to walk up to the Prime Minister, whoever that is, and say, mate, there's no way, right? There's just no way. You can't even predict what the surplus is going to be in 2 weeks. 10 years? You've got to be kidding me. And that's the way you've got to react when when you talk about prediction with time series. Be very careful. All right. Next thing to talk about is, this is one way to go, polynomial models. Polynomials are great, but here's a word for the wise. Linear's okay, quadratic's okay, cubic's okay, quartic, so that's a fourth order polynomial, it's okay. Fifth order polynomials, they're very wiggly. They're very wiggly. You wouldn't like them. And the thing is, as you get to bigger and bigger order polynomials, when they finish turning, they go either straight up or straight down, and predictions get very bad very quickly. So my best advice to you would be, and again, every rule there are exceptions to, but the rule I apply is, if you're fitting a fifth or higher order polynomial, you probably ought to stop. Right? Don't do it. And if you're going to go to a fourth order polynomial, think hard about whether it's a good idea. Because remember, these things, they have a fixed number of turning points and then they start to accelerate away from where they were, and that's not good. So that's one approach to fitting simple trends, is a polynomial model. Really easy to do. Now I'm going to show you very quickly another approach to fitting trends that's quite interesting, and that's the idea of using differences. Differencing. So differencing is quite cool. So to start us off, let's suppose that the trend was a linear trend. So let's suppose that the truth was trend is A plus B times time. Now, that's not what we got here. Here we've got a cubic, but let's suppose it was linear. Okay? So we're going to say xt is equal to A plus B times time. Okay, that's x at time t. Now let's take differences. Diff of x, which is x at time t minus x at time t minus 1. Okay, so it's basically taking a first order lag. X now minus x one time period ago. What would that look like? Well, let's do it. It's A plus B times t minus A plus B times t minus 1. Right? Which is A minus A plus B times t minus B times t plus B. Okay? Which equals A minus A is 0, BT minus BT is 0, this just equals B. Which doesn't depend on time, it's constant. So if your trend is linear and you take first differences, then it flattens out and becomes constant. Okay, cool. All right, what if your trend was quadratic? Okay, so now let's suppose x at time t is A plus bt plus ct squared. Okay, now let's do this again. Diff of x is equal to xt minus 1, so that's A plus bt plus ct squared minus, got a capital T in there, didn't mean to, A plus b times t minus 1 plus c times t minus 1 squared. Okay, what's going to happen to that? Well, you look at it, the a's are going to cancel, right? The bt's are going to cancel, leaving a b. T minus 1 all squared is t squared minus 2t plus 1, right? So your ct squareds are going to cancel. You're going to be left with a 2ct and a c. So this is equal to d plus e times t, the suitable values of d and e. Okay? So, I know I did that algebra on the fly, that's cool. Algebra is not a spectator sport. You do it at home if you want. But what happens is the top term disappears, the square term goes, it cancels. So, if you've got a polynomial trend, the highest order term will disappear when you take first differences.